Hi, I'm Zoe. This is my Physics 2 Lab 2. For the introduction, the purpose is to produce a computational model of two charged tapes exerting an electric force on each other, and then we're using this model to estimate the amount of charge on each tape necessary to float one above the other. So it's basically the same thing that we did in Lab 1, except this time we're distributing the charge evenly across the length of the tape as opposed to treating it as a point charge. So this is the formula for an electric field. Um, Basically this is K, which is the constant, and this is Q, which is the source charge, and then this is R, which is the observation location minus the source location. But this is magnitude of R squared. So magnitude of observation location minus the source location, and this is our hat, which is just R divided by the magnitude of R. And the main result was that we found the magnitude of the electric force and gravitational force using the distributed charge. So these are some assumptions we're making. We're ignoring the air resistance on a moving object. We're assuming that each U-tape we made had about the same amount of charge, evenly distributed along the length of the tape, and this is just like an example of a strip of tape that we would use in the lab. Oh, so this is a computational model. This is kind of what it looks like. So possible error would just be errors that I made in the code. So starting off, I'll show you the rest of the code later, but this is kind of what we did in lab 0. It's just a thing for the E field, so a function for the electric field. And so you can see basically use this formula, and we have Q, we have R, magnitude of R hat, and then the UFPES stands for K, so you just follow that same formula. Calculate, and then here's some of the, you can see the value of K is 9 times 10 to the 9th. This is the value of gravity, the gravitational, yeah. Then we have the mass of the tape and the estimated net charge on the tape, which we calculated previously, and the distance apart, which is 0.02 meters. And then this is the thing I was just explaining. And then this is creating the tapes, and you can see you're supposed to edit the Y, so put the distance apart. This is creating the arrows for the electric field. This is also creating the arrow, and it's the E scale minus. So it's like the scale times the electric field, because that's what we're trying to portray. And then, yeah, it's just kind of creating this is the electric force vector, and then you have to edit the axis to create another arrow, and then this is gravitational force vector. We're editing the axis to create the arrow. Here, so the white arrow is the electric force, and the yellow arrow is the gravitational force, which you can see in the code here. So, yeah. What if we did it as a single point charge, it would result in a charge that's smaller than when you distribute the charge. And then these estimates differ. Basically, I mean, kind of similar. One is smaller, one is larger, and the line charge estimate would be more accurate because each tape is an extended object. So like the assumptions that you make for the point charge will make it more inaccurate.